This computer. Welcome everyone to the Recurrent ETDS seminar. So today we have the great pleasure of listening to Thierry Delarue. I hope I pronounced this correctly this time.
Yes.
And he'll be telling us about sequences orthogonal to a class of dynamical systems. So over to you.
Okay, so thank you very much, Nishant, for the invitation, and thank you everyone for being here. Okay, so the work I will present today is based on joint papers with my colleagues, Martina Górska, Joanna Kułagap-Szymus, and Mariusz Lemańczyk from Toruń in Poland, and Adam Kanigowski from the University of Maryland. Okay, so the starting point of our research, maybe it doesn't work. Wait, sorry.
No, I think it's okay. I can see the pointer.
Yeah, but I can't change my slide.
Oh,
Okay. Okay, now it's okay. Okay, so the initial motivation for our work is conjecture formulated by Peter Sarnak in 2010. And this conjecture concerned the Möbius function. Okay, so the Möbius function is a very well-known function in number theory, which is defined on the natural integers, and it takes values -1, 0, or 1, and it is defined as follows. So mu of n is 0 if n is divisible by the square of a prime number, and otherwise, so n is then a product of distinct prime numbers, and the value of the Möbius function on n is then -1 to the power k, when k is the number of the prime divisors of n. Okay, so this function is very important in number theory. And for us, so it will be relevant to observe that we can decompose mu as the product of two functions. The first one is the lambda, which is the Liouville function, and the other one is just the square of the Möbius function. So lambda, the Liouville function, is defined as lambda of n is -1 to the power of the sum of the prime divisors of n, counted with multiplicity. And mu square, you can interpret it as the indicator function of the set of square free numbers that sets which are not divisible by squares of primes. Okay. And so this function, the behavior of the -1 on the one in the Möbius function is very chaotic. And it is so chaotic that specialists of number theory have formulated what is called the Möbius randomness principle, which is a quite a vague statement. And it says that the Möbius function is so chaotic that it cannot correlate with any reasonably simple sequence psi. In the following sense, if I average the values of mu of n times psi of n, then these averages go to 0 as n go to infinity. Okay, so this is a vague statement because we have no details on what reasonably simple means. And this is what suggested Peter Sarnak. He suggested the following definition for a reasonably simple sequence. And that would be a sequence which can be generated by a deterministic dynamical system. It means that psi of n is something like f of t and x, where x is a point in a compact metric space X, and T is a homeomorphism on X, and F is a continuous function taking values in the complex numbers. And so f of T and X is then a sequence produced by a dynamical system. And we say that the dynamical system is deterministic if the topological entropy of of t is 0. Okay? So now we can formulate precisely what is Sarnak conjecture. So it is that mu has no correlation with any sequence psi which is generated by a deterministic dynamical system, that is a dynamical system with zero topological entropy. Okay. So this statement, so we wanted to understand better what it means, and it yields to the following general question. Um, if uh, if we are given a sequence, a bounded sequence of complex number, so say U, how could we characterize the absence of correlation between U and any sequence which is generated by a deterministic dynamical system, or maybe no correlation between U on any sequence generated by some dynamical system in some class or some general class of dynamical system? Okay, and this is this general question that I want to speak about today. Okay, so this gives me the opportunity to introduce the following notation. So C is a class of dynamical system, and we say that U is orthogonal to C if U has no correlation with any sequence produced by a dynamical system in a class C. Okay, so this notation will appear in all the talk. And in this notation, we can express Sarnak conjecture. It is that mu is orthogonal to the class CZE, which is a class of zero entropy dynamical systems. Okay. So before I go further,
Sorry, can you go back to the previous slide? I just want
yes,
to make sure I understand
okay.
this definition.
Yeah.
So C perp is the set of all
Okay, so CZE here it means the class of all topological dynamical
zero
systems
entropy
which are,
systems.
sorry?
Ah,
Yeah,
I
which
see.
have which has zero entropy, which has zero topological entropy. Okay.
I see. I see. I see. I see. Okay, thank you.
Okay, we can imagine that we want to understand what it means to be orthogonal to some abstract class of dynamical systems. Okay.
Mhm.
So before I go further into the details, I want to be more precise about the type of objects we are dealing with. So we have, in fact, three types of objects, and we have many connections between them that I want to explain now. So the first one, okay, we have already met this. This is bounded sequence of complex numbers. So I will call them in general U. And because they are bounded, I will assume that they take their values in the unit circle of the complex plane, which is noted by this big U here. Okay, the second type of object we have already met also. It is topological dynamical system. So it means a couple xt, where X is a compact metric space and T is a homeomorphism defined on X. And then the third type of object, which will be very important in our work, is a measure theoretic dynamical system. So this time the system is defined on a Polish space Z. And we have also a transformation, which is denoted by R here. So R is supposed to be bimeasurable and invertible. And we have a probability measure rho on the Borel sigma algebra of Z. And we assume that R preserves the probability measure rho. Okay. So the connection between all these types of objects are very important. So we have already seen, for example, that a topological dynamical system can produce a bounded sequence. Just to take any complex valued uh, bounded continuous function on X, and you take the values of f along an orbit of the transformation. By the way, something I forgot to mention. I will assume that all the sequences I have are indexed the, by Z. Okay, so they are B infinite. So if you start with a sequence like the Möbius function, for example, which is only defined on the natural integer, you can complete it arbitrarily on the negative integers. It will have no importance. Okay. So now if we have a bounded sequence U, you can also see it as living in a topological dynamical system. Namely, you take the compact space of all sequences taking their values in the complex unit disk. And the transformation on this is just a shift, which I will always be denoted by S. Okay. So I can always see a bounded sequence as a point in a topological dynamical system. Okay, so now the connection between topological dynamical system and measure theoretic dynamical systems. So if we have a topological dynamical system, you can always put a t-invariant probability measure on the Borel sigma algebra, and then you get a measure theoretic dynamical system. Okay, so I will tell you more details about what kind of t-invariant probability measure we will be interested in. And conversely, if you have a measure theoretic dynamical system, then you can always find a topological model of it. So by a topological model, I mean a topological dynamical system xt such that there exists a t-invariant probability measure, say mu, so that x mu t is isomorphic in the measure theoretic sense to the starting measure theoretic dynamical system Z rho R. Okay, and there are some topological models which have special properties, and at some point they are important in what we do. Okay, so I will tell you more about that later. And
So,
then the last, sorry,
so I
you
just
have a
a quick question, if that's okay.
Yeah.
Uh,
Mhm.
are we assuming that the integral of f is zero or not?
Nothing for now. I don't assume anything. Okay.
I see.
Okay. At some point, okay, it will be some consequence of some assumption, but
Mhm.
for now I don't assume anything. Okay.
And I see. So you define this CZE perp. Do we
Yeah.
even know it's non-empty? Is there some obvious
Okay.
sequence?
So maybe I will come back to this notation later.
Sure,
Okay.
sure. Sorry for the interruption.
No, okay, no problem. Okay, so the last connection, which is very important also, and, it is even central in our work, is the notion of Furstenberg system of a sequence, a bounded sequence. So when you have a bounded sequence U, an arbitrary bounded sequence, you can always define a Furstenberg system, which is some measure theoretic dynamical system, which encodes all the statistical properties of this sequence. Okay, so I will now tell you more about how you can construct Furstenberg system of a sequence. Okay?
Excuse me,
Yeah.
could you go back to the previous slide?
Yes, sure.
All right. When you said you can always construct a corresponding topological dynamical system for a measure theoretic system, is there like a canonical model for that?
Sorry?
Like, is there a canonical model for that? Like, given a measure theoretic system, you always have this
Yeah,
certain sort of topological
yeah,
dynamical system.
there are some certain sort of dynamical system which are, as you say, canonical. Okay, I will say some details about that at the end of the talk.
Okay.
Okay. Okay, so you have an arbitrary bounded sequence U, and you see it as a point of this shift space U to the Z. Okay, and on this shift space, of course, you have the action of S, the shift transformation. And then you can consider the positive orbit of U, and you take the n first points on this orbit, and you average the Dirac masses on this orbit, and this is what we call some empirical measure along the orbit of U. Okay, so this is some probability measure on U to the Z, and because U to the Z is a compact metric space, the space of all probability measure on U to the Z is also a compact metric space if you endow it with the weak topology. Okay, so here we have a sequence of empirical measures which live in a compact metric space, so we can always find a subsequence that converge to some limit. Okay, so this is what we do. So we can have a subsequence nk, so that this subsequence converge to some probability measure kappa, and this is a probability measure on the set of sequences. And because S is continuous, this probability measure kappa is always S invariant. Okay, so this defines a measure theoretic dynamical system, U to the Z, kappa S. On any measure theoretic dynamical system that we can get in this way, we call it a Furstenberg system of U. Okay. So in fact, I should have put a plural in the title of this slide, because in general, there is several Furstenberg system for a sequence, because it depends, of course, of the subsequence that you choose to define the limit. Okay. It can happen that the sequence has only one Furstenberg system. Okay. In this case, we say that the sequence is generic for the measure kappa, but in general, it has many Furstenberg systems. Okay. On this construction, in fact, we can do it in the context of an arbitrary point in an arbitrary topological dynamical system. So if I take a point X in a topological dynamical system xt, I can do the same. Okay, I extract some subsequence so that the empirical measures converge, and the limit defines a measure theoretic dynamical system, which I call a Furstenberg system of my point X in the dynamical system. Okay, so this is a general construction, and maybe I introduce the following notion. So any measure kappa that I get as a limit of this empirical measure, I will create a visible measure on the orbit of X. Okay. And if I take all visible measures for all points in the dynamical system, I will get all visible measures in the dynamical system. Okay. So in general, so all visible measures, of course, are T invariant, but in general, there are T invariant measures which are not visible. Okay, it can happen. Okay, so we are only interested in these visible measures. Okay, no question? Okay, so I will come back a little to Sarnak conjecture. In fact, I will go back to 1965, where there was this important conjecture formulated by Chaola. And this conjecture does not concern the Möbius function, but the Liouville function. And okay, Chaola formulated the conjecture in terms of correlations of the Liouville function, but I will formulate it in the following way. The Chaola conjecture is that lambda, the Liouville function, has a single Furstenberg system, and this single Furstenberg system is defined by the S invariant measure on U, which is just the product measure of uniform measures on 1 and -1s. Okay, so in other words, it means that if you take any finite sequence of 1s and -1s, say of length k, and if you measure the frequency with which this block will appear in the Liouville function, then this block will appear with a frequency of 1/2 to the k. Okay, so all block sequence will appear with the same frequency. Okay. And Sarnak observed in 2010 that if the Chao conjecture is valid, then we have the following property that the Liouville function is orthogonal to all topological system of zero entropy. Okay, the key ingredient to prove that is the following. You observe that the only Furstenberg system of the Liouville function is in fact a Bernoulli shift because all the coordinates are independent. Okay, and then we can use the following fact that Bernoulli shifts are disjoint from any system, any measure theoretic system of zero entropy. Okay, so maybe it's a good time to recall some facts about joinings and disjointness. So if I have two measure theoretic systems, R1 and R2, acting on Z1 and Z2, then I can construct the product system. So I am on the Cartesian product Z1 times Z2, and I consider the product action R1 times R2. And then I take a probability measure on the product space, and I say that rho is a joining of the two systems if it satisfies the following. So first of all, rho should be invariant by the product action. And then the marginals of rho should be rho1 and rho2. That is the initial probability measures that we had. And finally, we define by G of R1, R2, the set of all the joinings of two systems. Okay, and this set of joinings is never empty because you can always have the product measure in this set. Okay, but it can happen that you have only the product measure, and in that case, we say that the two systems are disjoint. There are no other way to join them together than with the product measure. Okay, and one of the first results about disjointness, which have been proved by Furstenberg, is that Bernoulli shifts are disjoint from systems of zero entropy. Okay. And this is the key to prove that the Chao conjecture implies that the Liouville function is orthogonal to a zero entropy system. But then, in fact, Sarnak proved the following more general result, that the Chao conjecture also implies that the Möbius function itself is orthogonal to the class of zero entropy system. And this is more surprising because if you take any Furstenberg system of the Möbius function, then any Furstenberg system of mu has always a zero entropy factor. And this factor is obtained by forgetting about the signs of the -1s and the 1s. Okay, so in fact, you just consider the square of the Möbius function. And the square of the Möbius function is much more easy to study. And it turns out that the square of the Möbius function has only one Furstenberg system that we know. And this Furstenberg system is defined by this measure kappa m, which is called the Mirsky measure. And this defines a system of zero entropy. In fact, it is a point spectrum system. Okay, it is a discrete spectrum system. So any Furstenberg system of the Möbius function must have this zero entropy system as a factor. So it is no more true that the Furstenberg system of U are disjoint from zero entropy systems. Okay, so we want to understand better why the Chao conjecture implies that mu is orthogonal to the class of zero entropy. That is, it implies the Sarnak conjecture. And the reason, okay, I will just sketch the reason why it is still true that Chao implies Sarnak. So I recall you that Chao conjecture means that the Liouville function has only one Furstenberg system. And we can show that if the Chao-La conjecture is true, then in fact, mu, the Möbius function, also has only one Furstenberg system. Okay? For that, you just use the fact that mu is the product of the Liouville function with the square of the Möbius function. So we know that mu square has only one Furstenberg system, which is of zero entropy. And the Liouville function, by assumption, has only one Furstenberg system, which is Bernoulli shift. And then you use the fact that these two systems are disjoint, and you get that necessarily mu has only one Furstenberg system. Okay, and we can describe quite well this Furstenberg system. And then we can show that in this Furstenberg system, Xi1, which is the coordinate one in the space of sequences, is orthogonal to the Pinsker factor sigma algebra in this Furstenberg system. Okay, that is the conditional expectation of Xi1 with respect to the Pinsker factor is 0. Okay, and maybe I forgot to put equal 0. Okay, sorry. So I should have put the conditional expectation equals 0 here. And then this property implies, I will show you later why, that mu is orthogonal to the class of zero entropy systems. Okay? So this is the sketch of the proof that Chao-La implies Sarnak. And then William Veitch came with the following conjecture, which is a kind of intermediate between the Chao-La and the Sarnak conjecture. Okay, so Veitch conjectures the following. Okay, so maybe it is not true that the Liouville function has only one Furstenberg system, and maybe it is not true that the Möbius function has only one Furstenberg system. But in any case, for any Furstenberg system kappa of the Möbius function, the coordinate one in this Furstenberg system is orthogonal to the Pinsker factor sigma algebra. Okay, and this would imply that the Sarnak conjecture is true anyway. Okay, so this is the conjecture, which is now the starting point of what we did after. Okay, so this conjecture is formulated in terms of the Möbius function. But we decided to study this property in a more abstract setting. So we defined to define the Veitch property with respect to the zero entropy as follows. So I have a bounded sequence U, and I say that U satisfies the Veitch property with respect to the zero entropy property if the following is true for any Furstenberg system of U. In this Furstenberg system, the coordinate one is orthogonal to the Pinsker sigma algebra. That is the conditional expectation with respect to the Pinsker factor sigma algebra vanishes. Okay, so this is the definition of the Veitch property. And so I will show you a bit later why, in general, the Veitch property for a bounded sequence U implies that this sequence must be orthogonal to the class of zero entropy system. Okay? But before that, I will try to explain why we can replace the zero entropy property in this setting by some other classes of dynamical systems. Okay? But for that, we have to be careful because in the definition of the Veitch property, there is the Pinsker sigma algebra, which plays a very important role. And okay, we have to generalize this sigma algebra and see when we can define the analog of the Pinsker sigma algebra. Okay, for which properties can we do this? And this is precisely the role of.
Can you go back to the previous slide?
Yes, sure.
So this is the definition of the Veitch property, right?
Yeah.
So I just want to make sure I understand. So you're saying that so Weech property of Z, so this is all sequences which satisfy the Weech property.
Yeah.
And you're saying that I just want to make sure I understand the definition for all
All Furstenberg system of the
Furstenberg systems
sequence
from mu, we want
from U, yes. We have that the coordinate one. So the Furstenberg system is defined on the Schiff space of all sequences.
your
Okay. And in this systems, I have that the coordinate one is orthogonal to the Pinsker sigma algebra.
answers.
Okay. Is that clear?
I see. And this is so you only look at the ones which arise from the Furstenberg systems from mu, and then you take the conditional expectation with respect to the Pinsker sigma algebra, and I think I understand. Thank you.
You see that?
Yes.
Okay. Okay. So I introduce now the notion of characteristic class. So by this, I mean a class of measure theoretic dynamical system. I will denote it by F. And I say that F is a characteristic class if it is stable by the following operation. So first, it is stable by taking isomorphisms. It is stable by taking factors. That means if I have a system which is in the class F, and if I have a factor of this system, then the factor is also in the class F. And the last one is that we require F to be stable by taking countable joinings. So it means that if I have a countable family of systems which are all in the class F, and if I take a joining of all these systems together, then the joining defines again a measure theoretic dynamical system which is in the class F. Okay? So this is the notion of characteristic class. Okay? So there are many classical examples of characteristic classes, and the first one, of course, is the class of zero-entropy measure theoretic systems. Okay, it is quite easy to see that it is, of course, stable by isomorphism, taking factors and countable joinings. But there are also many other classical examples. So for example, so maybe this one is kind of curious. The class of all identities is also a characteristic class. Okay, this one is also interesting. So you can take the class of all measure theoretic dynamical systems which have discrete spectra, and this is also a characteristic class. You have these nil S classes, which are the class of all measure theoretic dynamical system whose ergodic components are S-steps nil systems. Another interesting example is given by the following. So you can consider the class rig of Qn. So Qn is a sequence of integers going to infinity, and you take all the systems which are rigid along this sequence. And this gives you a characteristic class also. Okay. And the fact is that in all these kind of characteristic class, we can generalize the notion of Pinsker sigma algebra. Okay. In the following sense. So in every measure theoretic system, if I have a characteristic class F, then there exists a largest F factor, which I denote by AF, in the Borel sigma algebra. So by this, I mean the following. So largest is in the sense of inclusion of sigma algebras. So I take all the sub-sigma algebras of the Borel sigma algebra, which are invariant by the transformation, and which define a measure theoretic dynamical system, which is in the class F. And this is not empty. And we can always take the largest such sigma algebra. Okay, it always exists. So for the classical examples that I gave you, for example, if you take the class of zero-entropy systems, then of course the largest F factor is the Pinsker factor. If you take the class of identities, then the largest id factor is exactly the invariant factor. That means the sigma algebra of events which are invariant by the transformation. Okay. For the discrete spectrum class, the largest F factor is called the Kronecker factor. Okay, it is the factor which is generated by eigenfunctions of the systems. For the nil S class, then the largest F factor is usually denoted by ZS, and this is the structure factor in the post-class theory. Okay, so there are many examples of this kind of characteristic class, and sometimes it's not so obvious to identify the largest factor, but okay, it always exists.
So the existence is just some kind of Zorn's lemma?
Sorry. No, you don't need a Zorn lemma. You take all exactly you repeat the definition of the Pinsker, the construction of the Pinsker factor.
Uh-huh.
In fact, if you analyze
Sure.
how you construct the Pinsker factor, the construction works for any characteristic class.
Sure. I think I understand.
And then this largest F factor has it plays a very important role because of the following. It controls all the joinings between an arbitrary measure theoretic system and any system which is in the class F. Okay? And the control are as follows. So I take an arbitrary system Z rho R, okay? And inside this system, I have the largest F factor, AF. And then I take another system, which I assume to be an F system, a system in the class F. Okay. Now I take any joining between R and this F system T. Okay. And this joining always satisfies the following. If in the system Z rho R, I take an L2 function which satisfies that the conditional expectation of f with respect to the largest f factor is 0. Then in the joining, this function f of z will always be orthogonal to any function of y. Okay? So it means that any non-trivial joining between z and an f system should pass through the largest f factor. Okay, if a function is orthogonal to this f factor, then it is orthogonal to any function in the f system. Okay. And then with this we can formulate the more general Witch property for an arbitrarily characteristic class F. So I say that U satisfies the Witch property with respect to F if for any Furstenberg system of U, in this Furstenberg system, the coordinate 1 is orthogonal to the largest F factor. Okay. So this generalizes the Witch property for the zero-entropy class, of course. And we also have this theorem that the Witch property with respect to the class F implies that the sequence U is orthogonal to all topological dynamical system in the class CF. But then I have to define what is this class CF, because F is a class of measure theoretic dynamical system. And then CF is the following. CF is the class of all topological systems whose all visible measures give rise to a measure theoretic system in the class F. Okay? So this if you take F as a class of zero-entropy system, zero-entropy measure theoretic system, then the class CZE will be exactly the class of topological system with zero topological entropy. Okay, so this makes sense, I hope. Okay, so now maybe I can give you the sketch of the proof why this Veitch property with respect to F implies that we are orthogonal to any system, topological system in CF.
So can you go to the previous slide?
Yes.
So in light of this, like given a topological dynamical system and you get all the visible measures from it, is there no structure to all the measure theoretic dynamical systems that you can form from that?
I'm
Because
sorry,
what this seems to be, I'm assuming what this seems to be implying is that you can have a topological dynamical systems and you can form a lot of measure theoretic dynamical systems using the visible measures which are not closed under the properties of your characteristic classes.
well, I don't know. Maybe you have many.
So is there any structure at all? Like,
In general, no.
oh,
If you take the shift space, the full shift,
hmm,
okay, you have anything that you want in the for visible measure. Okay.
I see.
But okay, in subsystem, you can say something, and you can say that only this kind of invariant measure will appear. Okay.
Okay.
Okay, so I will give you the sketch of why the Veitch property implies the orthogonality to CF. So I take a sequence U that satisfies the Veitch property with respect to the class F. So I take a topological system which is in CF. I take X in the space, and F a continuous function defined on X. And we want to prove the following convergence. If we average U of n times F of T n X, it goes to 0. Okay. So I consider the couple UX as a point in a product space, which is UZ times X, on which we consider the product transformation S times T. And then I can take a first-order system of this couple UX in this product system. Okay, so I take any sequence nk which defines the first-order system that if I have convergence of the empirical measures along this subsequence nk. Okay, and I call kappa the invariant measure, the visible invariant measure. And I can say some many things about kappa. Then the first thing is that kappa is a joining of two invariant measures, kappa u and kappa x. So kappa u is just obtained by taking just the first coordinate in this product space. And then you see that kappa u is, in fact, a first-order system of the sequence u. And then, for the same reason, kappa x defines a first-order system of the point x in the system. Okay? And then kappa, this first-order system of the pair ux, is necessarily a joining of kappa u on kappa x. Of kappa u on kappa x. Okay? And applying the definition of the weak convergence, which is the assumption here, we can see that if I average u of n times f of t n x along this subsequence nk, then in the limit, I will have the expectation with respect to kappa of the function xi1 times f. Okay? But by the Veitch property, I know that the conditional expectation of xi1 with respect to the largest f factor in the first-order system of U should be 0. Okay, this is the Veitch property for U. And on the other way, on the other side, because I assume that xt is a system in CF, then this first-order system defined by kappa x must be in the class CF because it is some measure visible in X. Okay. And then because this largest sigma F sigma algebra, it controls all the joinings between the first order system of U on all F systems, then I can conclude that this expectation is 0. Okay. And this is true for any sequence nk which gives rise to a first-order system. But okay, if I have any subsequence for which these averages don't go to zero, I can always extract a subsequence which defines the first-order system. And then where I see that along this sequence I have zero. So I think it proves that we are orthogonal to all systems in CF. Okay. So now the question is the converse true? That is, can we see if we are orthogonal to all systems in CF, is it true that the Veitch property is satisfied for the sequence? So is it an exact characterization of this orthogonality assumption? So it turns out that this is not always the case. And in fact, we have a counterexample with the class ReQN for a very special sequence QN. So this is the bad news, but the good news is that the converse is true for many good characteristic classes. And the good characteristic classes include in particular the class of zero-entropy systems. And this is nice because this allows you to state the following. The Veitch conjecture, which I stated before for the Möbius function, is in fact exactly equivalent to the Sarnak conjecture because the Veitch property is in fact equivalent in this setting to the property of being orthogonal to the class CZE. Okay. So now I want to precise what I mean by good characteristic class here. Okay. For which good characteristic class do we have the converse hold? So these are what we call EC classes. So I start with an arbitrary characteristic class of measure theoretic systems. And then I construct the class FEC, which is the class of all measure theoretic systems in which almost all ergodic components define systems in F. Okay, I just look at the ergodic component of my system and I check if the ergodic components are in F. Okay. And okay, this property is satisfied that FEC is always a characteristic class. And we say that F is an EC class is if F is equal to FEC.
Sorry,
Okay,
I'm
so
trying to understand this definition. So FEC are the class of measure theoretic systems in which all
so you
ergodic components are in F.
are in F
Ah,
because I started with an arbitrary characteristic class. Okay,
right, right.
and now I just look at the ergodic component and I'm just looking at whether these ergodic components are in F or not.
Uh-huh. Uh-huh.
And this is if this is true for almost all ergodic components, and I say that my system is in FEC. Okay,
But
and there is no general inclusion between F and FEC. Okay,
I see.
we have counterexample in both ways.
I see. I see. That's what I was.
Okay,
Okay.
but if you take the class of zero-entropy systems, then this is an EC class because a system is of zero entropy if and only if almost all ergodic components have zero entropy. Okay. Okay. If you start from any characteristic class F, then FEC is always an EC class also. And this is an example of a class which is not an EC class. So you take the class of system with discrete spectrum. And this is not an EC class because we have this counterexample. You take the system defined on the two-dimensional torus, and x, y is mapped to x plus y. Okay? So you can identify easily the ergodic components, and all the ergodic components give rise to rotations, maybe irrational rotations or finite rotations. But all these ergodic components have discrete spectrum. However, the whole system, it has continuous spectrum. Okay, so the class DISP is not an EC class. Okay, and then we have this theorem, and this one is much more difficult to prove than the other one, that if F is an EC class, then being orthogonal to the class CF is equivalent to the Veitch property with respect to F. Okay. So I will not show you all the details of the proof of this of the converse inclusion, but I would like to introduce you with three important tools in the proof because I think they are interesting in for themselves. Okay. And the first tool that I want to talk about is what we call the strong Momo property. So I start with the sequence U, which is orthogonal to all systems in CF. Okay, then it means that if I take a system in CF, a point X in the space on a continuous function, then I have the correlation between U and the sequence defined by F on X is 0. Okay. Then I introduce a subsequence of integers, bk, which is strictly increasing, and I assume that the gaps bk plus 1 minus bk go to infinity. Okay, and I just cut the sum into pieces from bk minus 1 to bk. Okay, so this, of course, this conversion still holds. But the fact is that if I assume that U is orthogonal to all systems in CF, then I have the stronger properties that I can change the orbit on the pieces from bk minus 1 to bk. That is, I take a sequence, an arbitrary sequence xk on x, and between bk minus 1 and bk, I consider the orbit of xk. And then this convergence is still true. Okay? And this is what we call the Momo property, and Momo stands for mean orthogonality on moving orbits. Okay, I change the orbit from time to time. Okay, and then the strong version of the Momo property means that we can even take absolute values in this box. Okay, and this is an important result is if you are orthogonal to all systems in CF, then in fact you satisfy a stronger form of orthogonality, which is the following one. Okay, so you have a kind of uniform convergence with respect to the function and to the sequence of points that you take. Okay. Okay, so this is the first tool. The second tool is about models of measure theoretic systems. So we spoke a little bit on that at the beginning of the talk, and it turns out that at some point we need some special models. So I think most of us are familiar with the Jewett-Krieger theorem, which says that if you take an ergodic measure theoretic system, then it always have a topological model which is uniquely ergodic. Okay, so this is a well-known theorem, but it turns out that we have a non-ergodic version of this Jewett-Krieger theorem, and this version was proved by Ansel in 1974. Okay, so I will state it as follows. So if you have now an arbitrary measure theoretic system, you don't assume that it is ergodic here, then you can always find a topological model which is a union of uniquely ergodic model. Okay, so you see the ergodic components in these uniquely ergodic models. Okay, and I will state it in the following way that in this topological model, every point X has a unique Furstenberg system. It is generic for a unique invariant measure. Okay, And this system is ergodic, of course. Okay, so this is more or less what Ansel proved in 1974. But in fact, we need a stronger version of this. And for this, we have to use a refinement of Ansel result, which was proved by Dovnarovich and Weiss in 2022. And Dovnarovich and Weiss have taken care of the zero measure set of ergodic components that can arise in these models, okay? Because a priori, it is not excluded that in this topological model, I have some zero measure ergodic components that does not satisfy what I wanted to satisfy, okay? But they came with a result that allow us to control what will happen in any ergodic component, yes, in any fiber of this model, okay? And with the result of Dovnarovich and Weiss, we can prove that if the measure theoretic system is in the EC class F, then I can take a model in which every Furstenberg system is also in the class F. Okay, I don't have to exclude the zero measure set of ergodic component. It is true for every ergodic component. Okay, and then the last tool that I want to talk about is the lifting result that we had to prove to prove the converse. And the lifting result is as follows. So I start with two topological dynamical systems, ys and xt. Then I take a point in the first one, so y is a point in y, and I take a subsequence that gives rise to a Furstenberg system kappa of y. Okay. And on the second system, I take any t invariant probability measure. I call it mu. So now I take a joining of y kappa s. So kappa is the Furstenberg system of little y, and mu is this t invariant probability measure on x, and I take a joining of them. And what I would like is, okay, I know that y is generic along the sequence nk for this marginal kappa, and I would like to lift the genericity of y in the product space. So could I find a point x in x such that the pair yx gives rise to a Furstenberg system which is rho? Okay. Okay. So this cannot happen in full generality because I have no assumption on mu. And I did not assume here that mu is a visible measure. So of course, in this setting, if I assume that yx is generic for the coupling rho, then in particular, x should have mu as a Furstenberg system. But I don't assume that mu is visible here. So if mu is not visible, this cannot happen. But what we have is the following. So even if it's not always true, then we have the following. So I can extract a subsequence nkl, and I can find a sequence xn of points in the space x. And this sequence xn is constituted of larger and larger pieces of orbits in the system. It means that xn plus 1 is almost always txn, except when n is a very sparse set of integers, b1, b2, and so on, with the gap going to infinity. Okay, so just from time to time, I change orbit, but otherwise, I just have long pieces of orbits in the system. Okay, and then with this sequence xn, I can recover the joining rows that I had at the beginning. Okay. And of course, this setting is convenient to work with the Momo properties that I had before. Okay. Okay, so I will not go into further detail for the proof, but okay, maybe if I have still a couple of minutes, I can.
Please go ahead.
Or I can give you some combinatorial interpretation of this Veach property for the class of zero-entropy system. So for that, I have to assume that U takes only finitely many values, because if this is the case, then I can say the following. For any Furstenberg system of U, then the Pinsker sigma algebra in the Furstenberg system can be seen as the tail sigma algebra of the process given by the coordinates in the Furstenberg system. Okay, so the Furstenberg system is defined on the set of sequences. So the coordinate define a stationary process, and then the Pinsker sigma algebra is defined as the tail sigma algebra of this process. Okay, and this is only true if the process takes only finitely many values. Okay, so then the Veach property means that the conditional expectation of psi1 with respect to the Pinsker sigma algebra vanishes. But this conditional sigma algebra, I can express it by the martingale theorem as the limit of the conditional expectation with respect to the sigma algebra generated by psi m plus 1, and so on. Okay, so this is a martingale theorem. And then the Veach property can be stated as follows. For any Furstenberg system of U, if I take the expectation of psi1 times some function, some bounded function by 1 of psi m plus 1, and so on. Okay, so in this expectation, I can replace psi1 by this conditional expectation, and this, of course, will go to 0 as m go to infinity. Okay, and maybe to simplify things, I can always take continuous function or function depending only on finitely many coordinates. And this will be exactly equivalent to the fact that this conditional expectation go to 0. Okay. And then I have just to interpret the fact that kappa is a Furstenberg system of U. Okay, and this can be stated as follows. For any sequence nk that gives rise to some Furstenberg system of U, and I have the following. The averages of U of n times f of U of n plus m, n plus m plus 1, and so on. So here f is an arbitrary function bounded by 1, which depends on only finitely many coordinates, and these averages must go to 0 as the gap m go to infinity. Okay, so this is quite ugly because okay, I have to introduce this sequence that gives rise to a Furstenberg system, but otherwise I think it's quite the best that we can do. Okay, so maybe I stop here. So if you have questions, thank you for your attention.
Thank the speaker. Questions?
Right. I'm still a bit confused about why you're taking the conditional expectation with respect to that particular sigma algebra.
So what is your question?
So I'm a bit confused about why whenever you're taking the conditional expectation is with respect to that particular sigma algebra,
To which sigma algebra?
mixed sigma algebra.
Hmm?
When you take E kappa with respect to
Which slide,
You're
Kinjal? Which slide are you mentioning?
here also, like every time
on this
it's
slide. Yeah.
yeah.
Okay, so what?
So like, is there any heuristic way of seeing like why you're doing that?
I don't understand at which point you don't understand.
That conditional expectation. Oh,
With
why
respect to
have
the
you always?
P-square,
Yeah. What's
this
the
one, you mean
right?
this one. So this one is just because of the Veitch property. The Veitch property says that in any Furstenberg system, the conditional expectation of the first coordinate psi1 should be, with respect to the P-square algebra, should be 0. So I'm just trying to interpret what is this conditional expectation here. And then I use the fact that the P-square algebra is the intersection of all these sigma algebras,
Hmm.
and I use the martingale theorem
Right. Okay.
to say that this is given by this limit here.
Yeah.
Okay?
All right. Yeah.
Other questions? Go. Someone was going to ask a question, maybe.
Oh, no, no. I would just like to thank Thierry. I mean, it's a very wonderful lecture. I mean,
Thank you very
I
much.
really liked it.
Thank you very much.
So I had another question. So if I understand this, an interesting correspondence where suppose someone gives us a sequence.
Mhm.
Using the sequence, I look at all visual measures that I get from that
Mhm.
sequence. And actually, maybe that's not the right way to go about it. Let's start with the sequence. Now I look at all measures which are disjoint from the sequence, in the sense that if I take any function, then the functional values are, decorrelate with the sequence.
Mhm. Mhm.
And then, so this class of measures that we get, measure preserving systems that we get, it's clearly closed under factors. I don't know if it is closed under joinings. Is this clear that it is closed under joinings?
Okay. Can you repeat again how you
So
define the
suppose
class?
I take a sequence, a bounded sequence,
Okay.
say even the Möbius function if you want.
Uh-huh.
And now let's look at the space of all measure preserving systems,
Mhm.
such that given any, say, L1 function or L infinity function on that for
Mhm.
that probability preserving system,
Mhm.
the values of the function decorrelates with this. Okay, take a
Mhm.
topological
Okay.
model just to
Model.
make sure
Okay.
that the functional
Okay.
values make sense.
Okay.
Uh, uh, this class of measure preserving systems that we get this way,
Mhm.
is this a characteristic class? Is this obvious? Is this
Oh, I know.
false?
I'm not sure it is true. No. Okay. I can't.
Because joinings are the problem, and of
Yeah.
course
Yeah.
also
Okay.
ergodic components are also a problem. And
Mm.
if you want to do FEC, and I was trying to see if there's some
No. No.
correspondence that
On
we
this.
can build.
Okay. I'm not sure if this is true. No. No. I don't think in general that it is a characteristic class. Maybe.
Right.
Okay.
But
I can't.
but it is closed under factors. So there is some
Mhm.
structure,
Sure.
and
Sure.
it's not clear to me what kind
No.
of
No. The
structure it
problem
has.
is joining. Okay. Taking joining is the most difficult part of the
Yes, yes, yes.
characteristic class because
And
okay.
in your structure, taking joinings is clearly very important. And
Yeah. Of course it is. Yes. Yeah.
so there is some kind of correspondence, but
Mhm.
uh, yeah, it's not clear. Also, for zero entropy systems, okay, so one question that I asked initially, if I take xi to be the Möbius function,
Mhm.
then no, what was the question I wanted to ask? Right. So if I take the Bernoulli minus 1 comma 1 with half
Mhm.
probability, and if I take any sample from this process, that
Mhm.
is perpendicular to any that is orthogonal to any disjoint from
Uh,
any zero entropy system, and so
Almost
therefore,
every year, yeah.
yeah, so that sort of says that CZE of is non-empty. But do we have other non-trivial examples of sequences which are orthogonal, which are in CZE per?
Okay, it's difficult to give an explicit example, of course.
Uh-huh.
Okay.
I see. Okay, that's what I wanted.
Yeah, it's okay. It's almost the same. I've giving an explicit example of a normal number in base 10, for example.
I
So
see.
that's
I see. I see. I see. Yeah, it's like saying that is square root of 2 normal. That's what you're saying.
yeah, okay.
Okay. Yeah,
Yeah,
that's the kind
very
of.
difficult in general. You know that there are plenty of such sequences, but
Right.
giving an explicit one is very difficult.
Uh-huh. Uh-huh. Okay. This is extremely interesting. There was another question I had about your Momo property.
Mhm.
This you define a few slides ago. Can
Maybe
you
I
go
can go
back to
back to
that property?
yes, sure, sure. This one.
Yes, the strong Momo property, in fact. So this is a so is it in some sense we are taking some kind of speed up of the dynamical system and then looking at you know actually I'm not sure so it looks like a speed up but then it's not exactly, so how should I
Yes.
interpret the strong Momo property? Is there a natural, like I'm thinking about skew products,
Hmm?
but is this how this arises, or
Well, this Momo property appeared a few years ago when we were trying to understand the
Mhm,
Möbius orthogonality question. And okay, we realized that if the Möbius function is orthogonal to all zero-entropy systems, then it has to satisfy some stronger form of this orthogonality. And in fact, this generalizes to any arbitrary function. Okay,
mhm.
but I don't know how to interpret it.
In an ergodic theory sort of okay.
Okay, so to prove this Momo property, in fact, you have to take many systems in the class CF, and you say that your function is orthogonal to this system and this system, and you
I see.
construct particular. Okay, so you take this sequence xk, and from
Uh-huh.
this sequence, you construct a special system in the class F. Okay.
And it's essentially all you're allowed to do is take ergodic components, take joinings. These are the
Mhm.
only things that you're allowed to do, and somehow this property comes out.
Mhm.
Okay, extremely interesting.
Okay,
Okay.
thank you very much.
Other questions? Okay, let's thank the speaker again. Wonderful talk. And
Thank you again for your invitation.
yeah.